So what we did last week was essentially talking about this picture here. It took us an hour or so, and there was a lot of talk. This is going to change. From now on, what we're going to do for the next year pretty much is talking about END, encryption and decryption. This is in a nutshell, hochkomprimiert, this is what we're going to do, you know, like a one-sentence thing. And what we're going to do today is we look, and that's pretty much almost the only time in this whole one-year course, where we look at ancient ciphers. I mean ancient as in ancient, so really old. This is also called the Caesar Chiffre, you know, Asterix. Yeah, this is Shift ciphers, is Caesar cipher, and a fine cipher. In order to get there, what we mainly do the next 60 minutes is we talk about some math stuff here. Okay, so we mainly do mathematics, and then at the end, as motivation, we show some old ciphers. So we start. The first section of today is entitled Modular Arithmetic. Or the modular arithmetic. And of course, the question you should ask yourself, or a good professor should explain to you every time you learn something, is why in the world are we doing that? Who's interested, right? And what we're doing here is, or what the goal is, I'll answer that question in a minute. The goal is first, we want to do computation. Of course, you know, crypto is based on computation here. You have to do computation. A fancy term for computation is arithmetic, Berechnungen. So we have to do computations and this is a very, very general rule in modern cryptography, in finite sets. Endlichen Mengen. Okay? Pretty much all the sets you've encountered so far in school were infinite. Right? There were the natural numbers, the whole numbers, the rational numbers, the irrational numbers. The people are going to. Did they start torturing you already with complex numbers? Yeah. One thing that all these different algebraic sets have in common is that they are infinite sets. In crypto, in almost all cases, like 93.8%. So pretty much every time we do modern crypto, we have to deal with finite sets, and it turns out that often you need very special computational rules, and this is what we're going to do today. And why do we do that? You know, this was the motivational thing, is because all modern crypto algorithms are based on that, but not only modern ones, but also Julius Caesar, you know, 2,000 years ago. So, and now we're going to talk about finite sets, and this is, again, bear that in mind. If you stay in this IT security program here in Bochum, you're going to need the same stuff over and over and over again for the next 3 years or 5 years if you stay on for a master's. So we look at an example for a finite set in everyday life. Any ideas? Most things that we encounter, for instance, if you go to the bakery and you buy rolls, Brötchen, we don't have finite sets, right? You know, if you have to buy 2 Brötchen for your girlfriend and then 10 Brötchen for your family, these are 12 Brötchen. Everybody with me? 2 and 10 is 12. And if you have to bring Brötchen for everybody here in this room, you're bringing 388 Brötchen or something. Everybody with me? There is no finite, right? I mean, at some point the baker runs out of flour, of meal, but the number gets bigger. So there is no, we run into some limit, which limits the set of Brötchen. So, so baker doesn't work. What works? Any ideas? Any ideas? Look over there on the wall. Top. Guck, alle oben gucken, links. Here, that's why I looked on my watch. This is a good one, right? If I tell you, you know, now it's, let's say, 12 o'clock. if I tell you, let's meet in 20 hours, we will not meet, you will not do, it's 12 o'clock now, plus 20. Nobody will meet at 32 hours. You know what I'm saying? So everybody will say, oh, plus 20, it's modular 25. So we'll meet at 8 o'clock in the morning. And this is so ingrained in us, eingeschleift. Perfect. Thank you very much. So let's try to get the music on. Headset 2. Nö. Können Sie mich einigermaßen hören, wenn hier die Leute ruhig sind? Oben billige Plätze, alles klar. Dann lassen wir es aus. Okay. Okay. So what I'm going to say, the clock is finite, right? So we're used to that. And in order to visualize that, finite sets you can often very, very nicely visualize in a circle. And this is exactly what people discovered, 800 years ago, that it's pretty useful to arrange the time in some kind of a circular movement type of phase, Ziffernblatt. So that's a bad circle. You know what I mean, right? So so we have 12 o'clock, 0 o'clock here, if you wish. We have 12 o'clock here, and then you get the idea, right? Then we have 6, and it makes a whole, European type of 24-hour watch thing, and you can make it with 12 numbers too. This is fine. We have 3, 9, 15. The idea is, again, looking at our example, and this is kind of the funny arithmetic which exists in if we do clock arithmetic. If it's 12 o'clock and we want to meet 20 hours later, this is not 32. But what we do is we say 12 plus 20 is 32, and what happens here? So we are 12, right? And now we count 20 hours ahead of time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20 here. We go here, right? So we start here and we add 20 hours. So according to this watch, that we typically German children learn that in first grade, ersten Schuljahr, is 8, okay? Which does not hold in the bakery, right? If you go to the bakery and people tell you by 12 rolls and 20 rolls, you're supposed to bring 32 rolls back and not 8. I know it's a very laughable example, and what's the nice thing about it is we are super used to this, right? You go to the bakery, there is no doubt that you're supposed to bring 32 rolls. I mean, maybe you make a mistake with, and you think it's 33 or 31, but you add up. So we're completely used to that. The nice thing is we're also completely used to that. Again, since first grade, you're told this is how the watch works, right? This is how we do arithmetic. And now, but what you do in mathematics then, you only do arithmetic in this way here. And now what I want to tell you here is to do that more systematically. In order to make that mathematically right, to tell you already what we do is you just add mod 24 to that. Okay, and what we're going to do the next 80 minutes, 70 minutes, we're going to talk about this mod operator, modulus operator. I have to take that away from you. I'm sorry. Oh, maybe I'll leave that here. Okay, so how is the 32 and the 8 related here? I mean, what is the general rule? If I give you a number and I want to reduce that modulo 24, what do I do? Any idea? Yeah. The remainder, right, the remainder. So what you do is you take this number, you divide it, teilen, right? And you're not really interested, normally if you divide, we're interested how often does this number fit in here? You know, in this case, the 24 fits in 1. The only thing you're interested in is the remainder, the rest, right? And it turns out the remainder, the rest, is 8, okay? So this modulo operator is also remainder operator, or rest operator, whatever you want to call that. And what I'm going to tell you now, I give you a more formal definition of this modulo operator. So let the three integers a, r, and m, a, r und m, be element of Z, natürliche ganze Zahlen, and m is positive, and then we write A is, so this is not called equal, this is not called gleich, this is called equivalent. It's equivalent to or congruent R modulo M. And now comes actually the important thing. If M divides A minus R, i.e. das heißt, i.e. ist das heißt in Latin, and just a mathematical symbol for divides, if M divides A minus R. So this is just a new math notation. This bar, this strich here, okay, reads M divides A minus R. Okay. And this definition is very, very important. You have to know that by heart, auswendig wissen. What is this? So now what this boils down to, we have to look at these three numbers which actually have names. I should introduce the names at this point. This A actually doesn't, this is kind of the number we normally deal with. We want to reduce typically. This M is surprise, surprise, called the modulus, and R is called the remainder, the rest und modulus. So they're very rather similar names in German. That means if you deal with modular arithmetic, we have to really, what's kind of the important thing is really here. This if, when, this if clause, the if clause is important. So what we have to somehow look at is the difference between A minus R. We have to look at these differences and together and relate that to M. So let's look at a few examples. Let's say A is equal to 13, M is equal to 9, and what we would like to know is what is R. One trick you can do is, forget about this whole definition here, you do what we said before. You take 13 and you divide, okay? So how often does the modulus fit into the 13 here? Wie oft passt das rein? One time. Very good, very good. What is the rest? What is the remainder then? Very good. Okay. This is one way of doing it. And now let's check whether this is what we kind of did almost by intuition, because most of us have heard about modular reduction, whether this is in accordance with this definition. So we look at this difference. We look at a minus r. What is a is 13. The r we just freshly computed is 4. This is 9. And now what we have to check is this a minus r, is this divisible by 9? And of course, 9 is divisible by 9. So that works out, right? So that works. If you think by now I'm making a big fuss, großen Aufstand about something that is completely easy, you're wrong. Okay? What I'm going to show you in the next 20 minutes, that there's much more behind that than, let's divide and take the remainder, which is what my daughter Flora does now in 4th grade. Vierte Klasse. Okay? So this was 4th grade so far. So the next 30 minutes, we go beyond 4th grade. And there's some things I can tell you are super, super cool about that. Okay, just bear with me. And now what we're going to do, have some kind of intelligent discussion about the implications. And some implications are easy. We just did the easy stuff, but as I told, and Flora can do that, right? Flora does it in a class. We're going to talk more about stuff that are not obvious. But just looking at this definition and saying, I thought this is going to happen, you're lying. Okay, so I'm going to tell you increasingly more surprising results about that. So the first thing we want to investigate is, maybe call that 1a, is how do we compute the remainder? So computation of the remainder. So very typical situation is in applied cryptography. Again, this is an intro course, and intro really means applied cryptography usually. A very typical situation is that you want to compute some crypto algorithm, and you just freshly computed A. Somehow this is part of your crypto algorithm. You have a formula, you compute that, you get A out, you know the modulus. This is typically part of the crypto system, and you want to know what R is. So this example is a very typical situation in applied cryptography. So that means given is very often, in fact, A and M in Z als ganze Zahl. And now the question, how do we compute R systematically? So what we do is you write A, kind of you start this way. You write it this way, where A equals to blank, right? 3 Kästchen, right? Freilassen, 3 little square space. This is how you start. And now you do exactly what we did verbally before. You look how often does the M fit into the A, and there's a fancy term is Q for quotient, which we're not going to use much in this lecture. We're going to use it at some point again. Quotient. So it's in the beginning, you can ignore that. When we talk about Euclidean algorithm in a few weeks, in a few months, 3 months or so, we're going to use it. But the thing we are really interested in is R. Let's look at an example. And I know this seems really, really, really easy. Let's look at A is 42. It's maybe a little larger, and we look at a modulus equal to 9. So what we do now, if you want to have the remainder, we write that exactly in this form, and we ask ourselves, how often does the 9 fit into the 42 in order to get the quotient out? And what is the result? How often does the 9 fit in there? 4 mal, genau, 4 times. And what is the remainder? What's the rest here? 6, right? Okay, so from this we would conclude and now it's the thing that's not trivial anymore. So this works. But we can do very unpleasant things here. Okay? We can, maybe let's leave, but we can do more things. So this holds, but we can also do things that are very unpleasant. For instance, we can say, oh yeah, and here, maybe let's write that down, this is r equal to 6. If we do a check here, we check according to this definition. So we take a minus r, we take 42 minus r minus 6 is 36, right? And now what we have to do, we check 9 is, of course, divisible by 36. Everything's fine. Okay, so again, this was really easy and naheliegend, obvious. And now comes something that's not that obvious. For instance, what happens? We can also write this equation equal to t. Okay, and now my claim is, meine Behauptung ist, okay, from this it follows that the r is equal to 15, which is kind of strange, right? This is not the rule. Let's look how often the 9 fit into the 42, because it doesn't fit in 3 times, it fits in 4 times. What I'm just telling you here is, this equation still holds, right? Das ist 27 plus 15 is 42, that stimmt, right? So now we're going to look into the red box and look whether the definition holds. The check here is, again, we take 42, we subtract 15, which is 27, right? And now we have to check, does 9 divide 27? Of course it does. So what I want to see here is 200 faces that look a little bit confused, right? Well, what I just showed you here is the remainder is not unique. Okay? Das ist nicht eindeutig. According to this definition, there are many remainders. I'm going to show you now things that are worse, okay? But also, so here I went down, right? I subtracted 9 less, now increase the number of 9s. I say, okay, I do 5 times 9, that is 45. And which integer do I have to write down here so that this equation is fulfilled? So this is a true equation. You can use pocket calculator, iPhone, cloud computing. What do I have to write down there? -3, very good. So according to this statement, here the remainder can also take the value of -3. Let's go back into the definition, check. 42 minus minus 3 is plus 3. So this is 45. And again, we have to check, does 9 divide 45? Of course it does. So the big lesson learned here is the remainder is not unique. Der Rest ist nicht eindeutig. But things get better again. And now, from this like seemingly somewhat unusual observation, we get a lot of implication, viele Implikationen. So a lot of things follows from this here. So this is much deeper than just, we're just lucky with the stuff that's happening up there. So this is we're going to talk about equivalence class and equivalence classes. Okay. Let's first start with another set of examples that are somewhat smaller examples. A equals 12, m equals 5. And then what we see is that 12, this holds. This is kind of the normal thing, right? We look how often does the 5 fit into the 12. 2 times, we get a remainder of 2. But then we do the same funny thing here. We can also do 12 is also equivalent to 7. You can always, if you don't believe me, you can always check. You do must divide this difference here. 5 divides 12 minus 7. Here it's 5. This is check is 5 divides 12 minus 2. Right? 5 divides 10. 5 divides 5. We can also go into negative numbers here. Minus 3. If we do the check here, we have to look 12 minus 3, which is 5 divides 15. It works. Okay. So, and now we come up with a definition. The set, and kind of in the beginning we start with 2, 7, and in this direction it's minus 3. And what do those 3 numbers have in common? What is the distance from here to here? That's 5, right? And that's also 5. And you can continue that as a series. So this is 12, 15, and so forth. And also you can go into in the negative range here of numbers. So we look at this set. This is an infinite set. Danke. Okay, 17. So forms an Gänsefüßchen equivalence class. Modulo 5. And now comes the important additional sentence. All members of the class means all the numbers, all the elements that are in this class, everything that's in the curly brackets in den geschweiften Klammern here, all the members behave, bad job cleaning the board, behave equivalent modulo 5. Doesn't need a red box, it needs a white box here. And we're going to talk about this. This is really the coolest. The last sentence is super cool. You probably don't see that. It's this moment. We're going to see that in 10 minutes or so. There's really cool computational tricks we can play with. But let's first start with let's look at all equivalence classes modulo 5. Okay. The first class that we can generate starts with a 0 here, and then we go in the positive direction 0, 5, 10, and so forth, and in the other direction, the direction of negative numbers, also in steps of 5. And now two simple questions. How many elements are in this class here, in this geschweifte Klammern, this curly brackets? How many numbers are in here? Yeah. Infinite. Okay, unendlich viele. Everybody. So first question. Second question. Do we catch all integers? Does this set contains all integers? Yeah. Yes. No. Wrong answer. Okay. Next. Who has another? Does this come? Okay. What about the integer 7? Is there? It skips, right? It springt drüber, right? So 7 is not in, 8 is not in, 333 is not in, minus 519 is not in. There are many numbers are not in, but it's still in. Fine. So what I want to do now is, where is the number, let's say, where's the number 6? It's in a different equivalent class, right? So let's look at the next equivalent class. Again, this question is, how many members are in this second class here? Infinite. As here, do those two classes, right, A and B, do they contain all integers? No, right? 7, we still don't have the 7, for instance, right? So what do we do with the 7? Okay, there's probably another class, then the class that starts with the 2 here. And here you go in the negative direction. Again, a very large class, infinite number of members, blah, 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 blah. Do we have all? Well, we have the 7 now. So this question is answered. Are there numbers left that we don't have? Any examples? Which integer is not listed here? It's not in any of these 3 classes. Yeah, 8 is very good. So let's do in class for 8. We like 8. So. Are we there yet? Did we catch all integers? Or are some integers that we didn't? Yeah. No, an example? 4 is not part of it. Exactly. So let's do the 4. So now my question, so we have 5 classes here, obvious. Each class has obviously an infinite number of members. Did we catch all integers? Do we have all integers that exist in here? Yeah. Or if you say no, give me counterexample. Give me one number that's not in here, you will not find one, okay? So if you have been asleep, so far this is perfectly fine. You have to wake up the next 120 seconds. 2 Minuten, this is all I need from you for today. Be awake, be alert. Inklusive der viertletzten Reihe. Ja, Sie, genau. Ja, ja, alle aufwachen. Sehr gut, sehr gut. So this is now the important thing. This is not intuitive, nicht intuitiv. And it's super cool and super helpful. What I'm going to show you now, you're going to use at some point, starting about in December, you're going to use all the time in crypto, okay? So, first of all, ich habe gerade gesagt, 2 Minuten, super. What you will see, we do arithmetic, not always, but often with natural numbers. So often we do arithmetic from 0, 1, 2, 3, 4 up to infinity. But in reality, we reduce the set of infinite many numbers, for instance, in this case, if we do modulo 5, to only 5 elements. So what we really do from now on is, in this case, it's modulo 5, you only do arithmetic with 5 things, 5 numbers. Okay, so what does this mean? What is the implication? So let's maybe get away from this 0, 1, 2, 3, 4 using integers, but giving them a name. Let's call this A, B, C, D, E. And now the only thing we're doing, we're concentrating on this last sentence here. All members of the class behave equivalent modulo 5. So what does it mean? Let's look at like in your crypto system later on, you have to do a computation. And let's say the computation is 13 times 16 minus 8. Let's say you have to do that. You have to do that computation. Very typical scenario. And I'll tell you, let's do that without pocket calculator. Do that with mental arithmetic, with Kopfrechnen, right? And it's borderline not so nice, right? 13 großes mal 1, blah, 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 blah. So what happens here, 13 times 16, I give you the answer, is 208 minus 8 is 200. And now we want to have the result. And what is that? What is 200 modulo 5? Yeah. What's it? 40. Yeah, 40 would be one. No, 40 is the quotient. So this 4 is a good answer, but it's wrong. Where is this? You gave me this number. This is 40. What is the R? 0. Rest is null, right? It's rest. So this is 0. You know, I skipped ahead. I gave you this 208. This was really, you know, if you do that with mental arithmetic, with Kopfrechnen, it's a little painful. And now, everybody awake? Perfect. Now comes the trick. Forget about the integers. I give them numbers. I say I'm not doing arithmetic with these actual numbers. I'm doing arithmetic with A, B, C, D, and E. So in this, we look, where's the 13? Which set is the 13 in? D. Okay. So I call this D. The 16 is in where? B, right? 16 would be here. The 8 is where? Was the 8? D again, right? Okay. So, and now the cool thing is, you can do this arithmetic here, 13 times 16 minus 8, you get the correct result. But there's a smarter way of doing that. If you exploit ausnutzen the sentence, all members of the class behave equivalent. Alle Klassenelemente verhalten sich gleichartig. That means, now the implication, buckle up, schnallen Sie sich an now, okay? You don't have to use 13. Where's 13? Where's 13 here? You can use any other member of the class. And are there members that we like better than the 13 for mental arithmetic? Yeah, which one is probably a nicer one? 3, right? Use the smallest one. 16 is even better, right? What's a nice number? What's a nicer number than 16 in this set here? 1, exactly. And we can replace 8 by 3 again, right? Now things become easy, right? Oops, it's 0 again. You can use any other number. Let's maybe do something else, so maybe you believe me. You can even take negative ones. You can go into the where will be D? Let's pick the 8 at this point, right? I pick 8. I replace B by whatever, 6 maybe. And D, let's take a negative one. Instead of 3, instead of 8, I use minus 7. Okay. 8 mal 6 ist 48. Minus 7 is plus 7. It's 55. So what is the remainder if I divide 55 by 5? What's the rest? 0, okay. Great. Go back to sleep. That's it for today. That was the hard part. That was the cool, not the hard, that was the cool part of today. Very important application. You might vaguely remember last week I talked about this classification of cryptography, and there are two big types of algorithms, you know, up there, Alice and Bob, and we have encryption, decryption, and there are two big families of algorithms, namely symmetric cryptography and asymmetric cryptography. Most asymmetric crypto schemes, there are only like 3 different classes that are really important in practice. They are based, so first of all, they're based on modular arithmetic. So in a kind of the second half of the lecture, or the second third of the lecture, we'll deal with them. And the operation you almost always have to do is exponentiation. Exponentiation, mit Hochzahlen rechnen. So, and let's end this modular. So a very typical situation in public key cryptography is you have to compute this. This is what happens in your web browser if you get a secure connection to Facebook or to whatever, eBay, Amazon, Flickr. Give me Every time you do a secure connection, get HTTPS running, you do an exponentiation. With this little small difference, the numbers are not 3, 8, and 7, but they are 2,000 bits long, really long. That means doing this exponentiation is super slow, even for 2 gigahertz or 3 gigahertz laptops. This is really hard to do. So here you want to use all the arithmetic tricks, all the Rechen tricks you can have, and I'll show you now an example. So the first way you can do that, which is widely known as the dumb way, that's die dumme Methode, you actually do first the exponentiation. What is 3 raised to the power of 8? 3 to the 8, 3 hoch 8. That's getting hard here, right? I don't see any hands going up. This is not an easy problem. So this is 6,561, just as you thought it would be, right? We're not done yet. So first you have to do this really large exponentiation. And then you have to divide by 7, which is not easy either. So, and then it turns out that the result is 2. Okay? Again, this is a dumb way, and I want to show you an easy way of doing that. The second way is we go back to, I think it's 7th grade, siebte Klasse, where you do this stuff with Exponentialrechnung, rules for dealing with exponentials. And one thing that you can do this. Everybody with me? 7th grade, 5, 6 years back in time, you did this. What is 3 to the 4th? Can we do that in mentally? 3 mal 3 mal 3 mal 3. Or 3 mal 3 and then Quadrat. You can do that too. Any? Yeah. 81. Very good. So. Okay. So far, everybody with me, you could do that. If you now continue, if you do 81 by 81, you end up with this approach. We don't want to do that, right? And it would be really, this is one way of just big picture looking at that. Why is that stupid? We have an intermediate result, a Zwischenresult, 6,561. But what is the possible result space? What is the possible space that we can get if you reduce modulo 7, if you do this division trick? What is the maximum number you can give, the maximum remainder, if you divide by 7? Yeah, 6, right? 0, 1, 2, 3, 4, 5, 6 can come out. But suddenly we have these huge numbers in between, which we know later on we don't even need, right? So we get inside the algorithm, inside the computation, become really big, and later we have to compress again. So the question is, can we do something smarter? Any ideas? What do we do from here on? What is better than multiplying 81 by 81? And it has to do with this here. Any ideas? Yeah. Yeah, exactly. So what you do here, you replace 81 inside the algorithm, inside your steps, by the numbers that are in the equivalence class. Maybe that's confusing. So this is modulo 5, we do modulo 7. So replace 81 by another element in this modulo 7 equivalent class, right? So what I did here, for instance, from here to here, first I did 13 times 16 minus 8. What I did from here to here, I reduced 13 modulo 5. What I did from here to here, I reduced 16 modulo 5. What I did from here to here, within one equivalence class, you always reduce modulo 5, or you jump in steps of 5. So we do exactly the same here. Rather than dealing with really long numbers, we compress 81, we make it smaller. And you gave the students there gave exactly the right answer. How often does the 7 fit in the 81? Wie oft passt die 7 in die 81? 11 Mal, right? And 11 times 7 is 77. There is a remainder of 4. And now it becomes easy. 4 times 4 is 16. And now we have to, again, reduce 16 by 7. We can do that mentally in our head, right? It fits in twice. There's a And again, so this is coming up in RSA, in Diffie-Hellman. It's even coming up elliptic curve, something really wild. But we want to do essentially this type of approach to it. And there will be homework problems on that. So if you look at this here, now, of course, the question is, if you get a problem, if you get a homework problem, if you get a crypto problem, which one do we choose? We just saw here that we essentially have 3 lines, right? We have 13 times 16 minus 8. We have 3 times 1 minus 3. We have 8 minus 6 minus 7. And they all were correct. There's nothing, there isn't that one is better than the other one. So mathematically, they're all correct. But we need a convention, a Konvention, a Vereinbarung. And what we normally do in each class, we pick the smallest positive one, which is normally if you're looking for an example in a homework problem, in a exam, and also later on probably if you use this stuff in practice, normally by convention, we say this is the result. If in an exam, if instead of 0 it gives the result 10, we probably take 1 point off and everything is fine. Okay? So this is not that this is wrong, but just by convention, normally it's more convenient to deal with the smallest positive members of each equivalent class. So this was a very long first chapter of today, and now we go to some other weird mathematical stuff. We talk about rings. So what we did so far, this was very much kind of a practical, maybe number theoretical driven use of the modular operator. And now we can also look that in an algebraic views, and algebra deals often with sets. So we kind of look what happens here from a different viewpoint. Again, all the same stuff holds, but we kind of change our viewpoint, unsere Perspektive on that. And we start with a definition, which is the quotation marks, Gänsefüßchen, integering Can people read that? The integering the index m consists of, and we're going to talk more, who knows what a ring is in algebraic terms? Also wer weiß, was ein Ring, wer hat schon mal vom Ring gehört, mathematischer Ring? That's bad. Wer hat schon mal von einer Gruppe gehört? A group. Few people. Okay, this is kind of like the next higher structure up, higher level, next level up structure. So when we talk about this algebraic structure, what you typically want to have, and you're going to hear a lot about that in discrete mathematics next year. Okay, this is very rushed 15 minutes introduction to that stuff. What we typically want to have, if you talk about algebraic structures, you want to have a set of elements and some kind of arithmetic operation. So you want to have a set of elements, an ensemble of things, and you want to do computations with that. So number one, what I give you is I give you the set. Namely, the integer ring consists of the set of integers, and we call that Z index M, or Z index M, which is, and this is very easy. So what this is, what you see there in the orange, the red-orange column in der Spalte da. That means these are all the numbers 0, 1, 2, up to n minus 1. So this set of integers is going to come up over and over and over and over again in this lecture, and if you stay in data security, in your life. Okay? Very often, you know, where did I start today? Here. Computation in finite sets. And the most popular set, luckily in cryptography, modern cryptography, is exactly this set of integers, right? You start with integer 0, 1, 2, 3, you stop at m minus 1. So we have m numbers in here starting with 0. So this is the most popular set. We're going to use that all the time. And now the second thing I told you, it's not enough to have an ensemble of things. You also want to do computation with that. And this is kind of what distinguishes these different algebraic structures. Namely, in the case of rings, you have two operators. And operators is a really fancy, sehr schicker, angeberischer Ausdruck for two types of computation, two arithmetic operations. Two operators, which we call plus and times, mal, das ist ein Malpunkt, and times s dot t dot means such that, so dass, okay, so dass, such that. I write that out. I saw too many people didn't know what I was talking about. Okay, such that for all A, B, C in the M, the following holds. A plus B is equivalent to C mod M. And A times B is equivalent D mod M. Oh, I forgot D here. Okay, A, B, C, D. And now we have to look in our book. So let's hope that the that looks good, yeah. Okay, so now we're going to do something which I don't like to do from a pedagogical point of view, but it's otherwise we run into time problems. So this is normally you need like 2 weeks or so to do in mathematics, and we do that in 5 minutes. From this definition here, this is a definition, but then there is like übergeordnete Regeln, so they're like overshadowing rules that every ring has to fulfill. And later on in this course and in your program of study, you will encounter more rings. Okay, so there's, for instance, polynomials form a ring, matrices form a ring. So actually stuff you had in school, people never told you that this is an algebraic interpretation of this stuff. What I want to show you now is, so this is a list here. I don't know whether you can see that. At this point, the following properties of rings are important. This was I wrote 2 years ago. And I just want to briefly discuss that. What are the implications here? And this is without proof. Normally, you have to check at this kind. This is a list of rules, and you have to check that all the rules are fulfilled. We're not going to do that. Probably Marcus is going to do that a little bit in the help session, in the Übung. But we are just discussing them here. Okay. The first thing is called, we can add and multiply any two numbers, and the result is always in the ring, which makes sense. So, you want to, again, you have a set of elements, you want to do arithmetic, and what this really means, if you do arithmetic with them, the result is always a member of the ring, so you're not leaving the set. So this is called closure, or the ring is closed. Weiß jemand deutsches Wort, German word for that? Abgeschlossenheit. Okay, it's a mathematical term, it's abgeschlossen. But again, this is very intuitive, right? It would be stupid. We talk about the set of things we want to do arithmetic, and if you're not careful, suddenly you're outside. You want to stay in this thing, which is assured through the modular operator. Right? Remember the stupid example with the Brötchen here, right? Right? If you do 12 plus 20 is 32, you would leave the ring if our ring if m is 24. If you use the mod 24 modular operator, you're sure that your remainder is never larger than 23. Right? So this modular operator assures closure, Abgeschlossenheit. Addition and multiplication, so we have these two operations are associative, associative. So it doesn't, if you have a sequence of operation, it doesn't matter in which sequence you do that. So whether you compute B plus C first and then you add A, or whether you do A plus B and then C. Now it's getting a little bit interesting. There's a neutrales element, a neutral element, with respect to addition, which is very easy because this is exactly the neutral element they told you in elementary school, in der Grundschule, right? This is 0. Well, later on, we will have situations where the neutral element is really weird. Okay, right now it's not weird. Right now it's the 0. So we have a neutral element with respect to addition, and now it's probably the only thing where things are not completely, or only time where things are not completely obvious. And the neutral element is defined this way. A plus neutral element is equal to A, and it holds for all A. Now comes the thing where it's getting a little interesting. We're also interested in what's called the inverse. Okay? That means given an element A, we want to have an inverse, which we call minus A, here, such that A plus its inverse is equal to 0. Why 0? And be careful, be awake. This 0 is the neutral element from one bullet point above, right? Ein Punkt oben, okay? So you use the neutral element from here to define the inverse. Okay, why? Because that's the definition of a ring. Okay, so you need that. So this is still hopefully easy, okay? Now comes the only thing which is not very straightforward, okay? So these two bullet points, so from here to here, this is with respect to addition, but addition was only the first operation. Now we look into multiplication, and suddenly things start to become a little strange. Namely, first of all, you need a neutral element. Again, neutral element is defined such A times neutral element is equal to A. There's nothing strange about it. This is the 1. This is exactly the 1 you learned in 3rd grade. Dritte Klasse macht man in NRW Multiplikation. Okay? So this is exactly the 1 you're familiar with. If you look, what is Professor Parr talking about exactly the 1? Later on, we will talk about different things where the 1 element is something weird. Okay? Right now, it's easy. So, but now it's getting interesting. Now we want to have an inverse to an element A such that A times its inverse is equal to 1. Okay? And why is that weird? I'll show you now. Example for multiplicative inverses. M is equal to 9 as an example. And let's say first example alpha or 1, whatever you want to call that. Let's say A is equal to 2. And we would like to know what is the inverse of that element. What do? You follow this definition, which I highlighted. You know, in this dark highlighted. So we are looking for now 2 times the inverse of 2 is equal to 1 modulo 9. Okay. So probably our first reaction is, well, this is easy. You know, 2 minus raised to the power 2 to the minus 1 is 1/2 is 0.5, 0.5. That would be our first reason. And why is this complete nonsense and wrong and bad and people have been sleeping for an hour? Why is this completely stupid? It's not in the set. I mean, what is in the set? M, 0, 1, 2, 3, 4. And there's no, I didn't say 0, 0.5, 1. I skipped the 0.5 here, right? So it's not in the set. So this is really bad. So what we are looking for here is obviously a number from this ensemble. There is no 0.5 here, right? So we what we need is one number that we can place in here. So we're looking at 2 times something is equal to 1 mod 9. And which number is that? Now we have to try. That's the best thing we can do at this moment. What is, yep. 5 works. 2 times 5 is 10. 10 modulo 9 is 1. Exactly, so 5. So you can write at this point, you get this weird thing, the weird notation, a little bit weird. The inverse of 2 is equal to 5 mod 9. Okay? And this inverse there is no direct relation to what you normally do with integers in elementary school or even in gymnasium or so forth. So this is this follows from this weird definition here. Now comes this very important thing I'm going to tell you. It doesn't take long. So for 2 we find the 5. Now I can give you, here's an offer. I give you 1,000 euros if, 3 is maybe too easy. I can give. If you give me a number that fits in here such that this equation is fulfilled. So the question is, which number do I have to put in here, of course, coming from this set, that this is fulfilled? This die erfüllt ist, okay? And I give you 1,000 euros if you come up with an answer. Everybody eager, and the only thing you can do is obviously you can try 0. 6 times 0 is 0, doesn't work. You can try 1, 6 times 1 is 6, doesn't work. 2, 6 times 6 is 12, modulo 9 is 12, modulo 9 is 3, doesn't work. 3, 6 times 3 is 18. 18 modulo 9 is, you know, I'm not giving away €1,000 easily, so it doesn't work with any of the numbers, okay? Which is kind of pathological, but there's an easy test to catch those. There's an easy test to find that. You compute the GCD in Deutsch GGT, größter gemeinsamer Teiler, greatest common divisor, of the numbers you want to invert, so in this case 6, and the modulus. And what is this? What's the GCD of 6 and 9, the GGT von 6 und 9? The greatest integer that divides both numbers. Yeah, 3. Okay. So this is 3. Let's look at this example we had before here. What's the GCD of 5 and 9? 2, sorry. 2. What's the GCD of 2 and 9? What's the greatest integer that divides both numbers? 1, very good. So, and this is almost the rule. Namely, if the GCD of the number you want to invert and the modulus is 1, the inverse exists. It doesn't tell you which number. It doesn't tell you that it's a 5, but you know one of the numbers is the inverse. There is an inverse. If this holds, if it's not equal to 1, the inverse does not exist. No. Good. No, good question. No, doesn't have to do with the ringness of that. That's very good. So there was an excellent remark. So the nature of rings is you can always add, you can always subtract. Namely, subtraction is property here. Because there's always the inverse, means you can always subtract. Okay. You can always multiply, obviously. But taking the inverse, which is division in essence, doesn't only work sometimes. So, okay, so ring is this weird algebraic structure. You know, we have 4 basic operations. Plus, minus, times, and divide, or inverse, right? And in a ring, you have 3 of the 4. You have plus, you have minus, you have times, and you don't really have inverse or divide. You only have it sometimes, which is not much help, okay? Ring is 2 operation. What you will see later on in this class and in discrete mathematics, there's a group. A group is the kind of the smallest elementary structure. You have 2 operations, plus and minus. Ring, you get one more. You get multiplication. And then, of course, there are structures where you have all 4, plus, minus, times, and divide, which is called a field or corpor. Okay? This is kind of in the middle. Now comes, and I know we're running a little bit short on time because the stupid sound system didn't work. Now, and this is kind of the nice thing, or maybe weird thing. I think it's a nice thing. So we spent more than an hour on doing math using this modular operator and all this and rings and blah, 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 blah. It's very, very easy to build crypto system, at least simple crypto system. And that's what we're going to do now. So the third chapter, which these are like 5-minute chapters now, are very easy to do. So the idea is shift letters in shift the letters in the alphabet. So this is, I should have said that first. The Caesar cipher is one of, as the name suggests, one of these old ciphers, ancient ciphers. And I talked about it last week until very recently, until the 1970s, pretty much all crypto algorithms operated on letters and not on bits or decimal numbers. They didn't operate on numbers, they operated on letters. So, and one idea that people had, 2,000 years ago is to do something very simple. You just shift the letters in the alphabet. So, example. And the shift we call K for key. You will later, so the number of shifts is the key of the crypto system. So for instance, A is replaced by D, B is replaced by E, and so forth. W, V is replaced by lowercase z. X is replaced by A. Oh, yeah. This is where I went to ask you a question. So once we're at W, at V, this is Z is the last letter in the alphabet, right? We shift by 3, right? A, we go 3 letters ahead. A, B, C, D. B, 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 C, D, B, A, B, C, D, E, right? E. At the end of the alphabet, W, X, Y, Z. Now with X, we're running out of the alphabet, right? So what we do is, what I like to call, we wrap around, namely, we haven't used A, B, C in the beginning, so we start at the beginning again. So X becomes A, X, Y, becomes V, Y, and Z becomes C. Okay. That's kind of. Wrap around, umfalten, so this is somewhat wrap around, this is a little bit colloquial, umgangssprachlich. And the beauty is this wrapping around is done automatically in a very beautiful fashion with the modular operator, okay? And what is the number? What kind of, is this modulo 9 or modulo 24 or what do we, what is our intuition? Which number do we need here? 26, because the alphabet has 26 elements, 26 letters, at least the, not counting umlaute and other, and as sets and stuff. So, and now, in order to do that with all, you're wondering, how is that related to the modular operation? This is kind of the systematic way of doing that. So the first thing you have to do the mapping, you have to do encoding. So ABC, this is what you see here, table 1.3, up there, A becomes 0, B becomes 1, up to Z becomes 25 here, right? So let's do the first. And here's the encryption and decryption rule. So this is now very beautiful. And of course, Julius Caesar didn't do that. He didn't know about modular arithmetic. He knew that just this kind of this hand rule. But the nice thing is we can also describe that mathematically with this definition, namely saying the encryption is X plus a key. So you shift by K position, in this case by 3 position, and then you take modulo 26. And for decryption, surprise, surprise, you subtract the key modulo 26. This is what's happening here. And then, you see an example, for instance, here in the word attack in plain text becomes a cipher text Okay, so, and now we can just discuss that here. So what is our gut feeling or Bauchgefühl? Is this secure or not? No. I want to hear two attacks from you. Yeah. One is frequency analysis, which is what you did for your homework. By the way, who could decipher the homework? Who was successful? Everybody. Very good, very good. Frequency analysis work. Another possibility is, yeah, key search, which we call brute force attack. How many keys are here in the system? Look in there. How many? What's the key space? Yeah.
26.
26. We can do that literally by hand, right? You try all. It's here, right? It's K is element of Z26, right? So there are only 26 possible keys. This is not secure. So you have even two attacks that work very nicely. Don't do that. There will be homework problems on that. Very easy. This is CF is compare. So compare last week's homework. And the second attack is the brute force attack or a full key search. So and now we come to the next. So what should we do from here on? Okay, let's try to make the thing a little bit more difficult. And if you look at, and that's the beauty, if you describe that mathematically, this is a mathematical description. Maybe focus on this. Den, kann man das lesen, wenn ich das dunkel mache eigentlich? Oder? Yeah. No, we can. The question is the camera can do that. So we're looking at this here. So this equation describes how the plain text is combined with the key, and that's pretty much the simplest thing that we can do. We simply add. And now the affine cipher. This is chapter number 4 of today. Does this in a more complicated fashion, namely the affine cipher. Does the following. It takes, first of all, the key is split in two parts. So also it becomes the key space becomes larger because it's not only a number k, but it's two numbers. There's a number a and b. And what we do, we multiply the plain text. The plain text is x by a, and we add something. So we have a shift at the end, but before we do the shift, we also multiply. And of course, everything more 26. So that's the encryption rule. In order to decrypt, we have to compute y again, right? So what we do, you simply rewrite the equation here. So we do y minus b. It's a times x. And then you divide by a. And this is something important. Good that I'm doing that here. From now on, never ever again in your life use the Bruchstrich. Okay? Never again. You die if you do that. No, you're not. I'm not Harry Potter, so you're not going to die. But instead of writing okay, why is that? That has to do with this weird inverse computation. Okay, you can do that. This is still correct. There will be no penalty, keine Strafpunkt if you do that. You will get confused. Try to replace this division, this Bruchstrich, by multiplication with the inverse. Just a little friendly tip from me, and you're welcome to ignore me, but I wouldn't. So this would be the, if you rewrite that, x becomes so this becomes the affine cipher, affine Chiffre. Okay. I showed you there. Okay. And now there's one tricky thing where we have to pay attention here is, first of all, is the question is this Doppelkreuz here, this double whatever pound sign, is the means number of. So how many keys are in the system? What is the key space? Okay. Well, we have to look, how many A's and B's are in the system, and let's start with the easy one. How many B's can we choose here? Well, probably 0, 1, 2, 3, 4, up to 26, right? This is just the shift. So this is 26 B's are in the system. And the tricky question is, how many A's can we use? If you just look at the encryption equation, there doesn't seem to be any limitation, right? You can choose 0, 1, 2, 3, 4, 5, blah, blah, blah. If you look at the decryption equation, there comes a restriction into play. Does anyone know why we suddenly restricted with A here? And who knows that? This were people really awake. Yeah, you?
Because of the great compliance.
Great. Super great. Absolutely perfect answer. Where did I have this here? So we said, which I didn't even write down, the inverse only exists if this GCD condition is fulfilled. That means you can only use A. Condition for A is, this is very unordentlich, so GCD this is condition for A. Okay. So give me an example for an A that works, just as an example. Which integer can I plug in here so that this, yeah. What's that? 13, no. 13 doesn't work. Yeah. What's that?
27.
Yeah, but we restricted by 26. So another thing. Yeah. Alle Prim zu prime numbers work. Give me an example for a prime number.
No.
Third three answer. Okay. Well, I have time, so yeah, take it. Give more wrong answers. Yeah. What's that? 26. Another wrong answer. Excellent. So, yeah, 5 works. So it looks all odd numbers work, right? What about 13? No, what's the GCD of 13 and 26? 2, right? So you have restrictions here. And it turns out that the number of A's is equal to 12. Okay? So the key space, number of keys, is of course number of A values times number of B values. Number of A values is 12, number of B values is 26. Das ist 260 plus 252, 312, 312. Yep. What about security here? Any attacks? Again, I want to hear 2 attacks, yeah? Same as before. One that definitely works is brute force. 312 keys you can, I mean, by hands this is hard, this is getting a little hard, but with a PC this is very easy. What about letter frequency attack? Does this work?
It always works as long as you encode one letter always with the same.
Exactly. This is a fixed mapping, fixed encoding, right? For a given, if you fix the key, if you have a key A and B, if you give me a letter X, you always get the Y value out here, right? So this frequency preserving property is given here, even though you have somewhat complicated formula. Okay, so that's it for today.